So folks, we're continuing our exploration of some of these definitional terms. This one should go a little bit faster. If we have an nth order linear ODE, we want to be able to state whether or not it is homogeneous. And here is the definition. If it's possible, and this is one of those unsatisfying definitions, if it can be written in this form, we're going to say that the ODE is homogeneous. Now, I know that this can look like a large mess of letters here, and that's challenging as we push our notation. But you can see that we've written the left-hand side in that linear form, and in the right-hand side, where we would have an f of x, we have the value 0. So if you go back to our definition of a linear ODE, we said that this was the definition of an nth order linear ODE. And so we called this linear form, and we had this could be any expression involving x. So for example, this is a second order linear ODE. We put it into, it's already in linear form for us, and here the function that depends just upon the independent variable is the cosine of x. Specifically, it's not the 0 function. And so this function right here would not be homogeneous. Let's go look at these examples, which will clarify the same thing. Okay? So this is a second order, because the highest derivative showing up is 2, linear ODE. It's already in that linear form that we learned about in the first video. And it is homogeneous. And the reason why it's homogeneous is once we've put it into this linear form, the function on the right-hand side is the 0 function. Okay? So this is second order linear, non-homogeneous or non-homogeneous. Here the issue is that if once we put it into linear form, it's already in linear form, then we can see that the function on the right-hand side that depends just on the independent variable x is the natural log of x. Okay. Now be careful here, folks, because at this point I've had students incorrectly make the assumption and say if I see an equation set equal to 0, it's homogeneous. Remember, you first have to have put it into linear form before you can make that assumption or make that assertion. Maybe you can see it earlier, but this assumes that we've put it into linear form. So this is the example that I want to get at that I think really clarifies this. This ODE right here is not yet in linear form. It is a linear ODE, but I haven't written in the form that we talked about in the first video. If I did some rearranging and I rewrote it as e sub x y double prime plus 1 over x y prime, and now if I subtract over this xy term and then factor out the y, I would have plus the tangent of x minus x y is equal to 0. So now this looks like linear form where we've staggered it by terms going from the highest order derivative on down, and this is my y double prime term, my y prime term, my y term, and then the function on the right hand side here is 0. So do you see where you can get into trouble if you erroneously say, oh, if it's set equal to 0, it's homogeneous, and if it's not set equal to 0, it's non-homogeneous. That assumes that you first put it into linear form. For example, this function right here is not in linear form. If we were to put it into linear form, there's e sub x y double prime plus 1 over x y prime. I don't have a standalone y term, so if you wanted to represent it, you could represent it as 0y equals minus the tangent of x. And this is our f of x, which does not equal 0. So again, folks, contrary to how it might have initially looked, this is non-homogeneous, and this term is homogeneous, or this ODE is homogeneous. Let's look at this example. Why don't we even ask the question, is this ODE homogeneous or not? It doesn't even make sense to ask the question, is this ODE homogeneous? Because in order to be homogeneous, it first had to be linear. So this ODE is not linear. Why is it not linear? Here I'm taking the square root of the dependent variable y. Here I'm dividing the dependent variable y into the number 1. Those are both nonlinear operations, so this ODE is not linear. Try as you might, you won't be able to rearrange this ODE into linear form the way we were maybe able to do with C or D or some of these other examples. So this ODE is not linear. And because it's not linear, it doesn't even make sense to ask the question, is it homogeneous or not? Because to determine whether or not it's homogeneous, you first put it into this linear form, and then you ask yourself, what is the value of this function over here that depends just on the independent variable? Again, I find these definitions not very satisfying. They say if it can be written in a form, and there's a little bit of ambiguity there because it might take a lot of work to write it into the form to determine whether or not it's homogeneous or not. Okay. I would add, and I'm going to add this to here, folks, that we will have a different word, homogeneous or homogeneity. We will use that word a couple of different ways in this class. Right now we're using it as a way of further classifying linear ODEs, and that might be different from later uses of the word homogeneous.